thiol oxidation going on, for example, right? So, or somehow it's asked, then just feel free to say, okay, well, it's going to be 2 RSH, right? Even though on the exam it's going to be like given like 1 RSH molecule of some sort needs to be oxidized, right? So, but you need to like understand that it has to be 2, and then just kind of like draw 2 here, right? So like no big deal, because you need to ultimately balance the equation, right? So, because you have this disulfide, so 2 RS pieces together, so you need to start with the 2 RSH pieces, right? So from each of which you will remove the hydrogen to make those final products. So, and then water will be kind of like, it's a more complicated reaction here. We just kind of like know from the fact, from the experiment, right, that water is formed upon this oxidation. And then that's what like we agree to show, just like show the water as a byproduct, even though it doesn't quite, well, it balances technically, right? Because you have 2 H's from RSH, 1 oxygen from O, as like Lucas showed us, for example, and then you technically do get H, and O, right? So then for the heavy metal reactions, that's what we'll have. Again, 2 is the stoichiometry coefficient, so that's term here that kind of like we recycle a lot. So then we'll have M2 plus, so it's going to be some kind of heavy metal ion, so maybe Pb2 plus, right? So, or it could be, what else? Hg, so that's the one here in the periodic table. You can find Hg somewhere in the periodic table. It's mercury, right? In like other words. So these are our options, Pb and Hg. These are like a letter. Pb, it's lead, right? So that's in the 4th column, by the way. Hg is next, actually, it's like to the left from lead. Lead is 82 number and Hg is 80. It's blue, right? For some reason. So it's like a liquid metal, maybe that's why. And yeah, so it also can react in this fashion. So yeah, in this case, you're going to break the SH bond and twice and make this kind of like metal S. Bonds will be formed that will like help to make this product, right? So it's going to be some kind of like organometallic compound, actually, right? So that's what we might call it. So because it combines literally organic stuff and metallic, right? Or metal, so organometallic, like maybe new term for somebody. So like quite exciting. So, and then that's it. So that's your like summary of the reactions, right? So maybe you can like draw that on the whiteboard in the library or something like that. So yeah, maybe print it out and put it on your wall, for instance, in the room. Some people do that, and then they say, okay, well, it's a nice background or like wallpaper, right? So that could be the way to go, or maybe not. So now let's see. Now we're going to continue with the next part, which is going to be which is going to be this one, right? So that's the cat slide, and it works actually on the big screen, so like quite nice. So now let's take a look at the new chapter, right? So which will start today. So it's going to be about aldehydes and ketones. So we saw already ketones and aldehydes previously, right? So maybe let's try to recall that. Where did we see them before, right? So it's a little bit of the review, and then hopefully this question will try to prompt you to connect your like previous knowledge with the new steps, right? So let's take a look. So how did we see ketones, for example, before, right? So in what sense? So that's a strangely formed question, but basically the question is like, how did you encounter ketones, right? In what way? So actually, so here is your hint, right? So that's potentially going to be some kind of like guide for you. So that's how you encounter ketones before, right? So, and then now we are going to like look at the entire chapter about ketones and aldehydes. So we did see them before, but maybe under what circumstances, right? More specifically. So let's see what we have. So we have some answers already flowing in. So good effort here. So how did we see ketones before, right? So that's the question for the moment. So like what were the circumstances, right? So if you look at this, you can definitely see the ketone, right? So because at this point you are like proficient in reading the skeletal structures, like people were using skeletal structures very nicely here. So that's a good job. So then what else? And yeah, you can see the ketone functional group here. So if you just like circle the respective atoms. Okay, well, we have a bunch of responses already, so that's quite excellent. So if you take at this example, for example, here we have carbon, then we have carbon O and another carbon. So that's this like red region. So that's going to be your C, CO, and C, right? So that's the one. So you have the ketone in this case. So then what do people think, right, about, okay, so there are like very nice responses such as oxidation of the secondary alcohol, right? So that's great. So, or you have in the middle of a carbon chain, right? So like here, so that's kind of like in, or it must be like in the middle. The ketone cannot be on the end of the carbon chain. It is somewhere in the middle, kind of, right? So not necessarily in the like dead in the middle. So, but it can be like on the edge, right? So as opposed to an aldehyde, for instance. So that's a good observation here. So secondary oxidation, like secondary alcohol oxidation, right? So yeah, all right, so good. So like looks like people kind of try to make the connection with the past, so which is nice. And now let's take a look at what the ketones and aldehydes are about, right? So we have the important next thing here, which we encountered already. So, but we might as well review that, right? So that's the so-called carbonyl group, bless you. So yeah, basically what you need to have, so if you were to show the carbons and such explicitly, so here we go, right? So like for the carbonyl, you need to have the carbon, like that, double bonded to oxygen, right? So that's going to be your carbonyl group. So that's how you can represent it. And here you have like something, right? So like whatever it might be. So typically for now, so we can have two options here, right? So we can have, for example, C and C instead of those squiggles. In this case, you're going to have the ketone functional group, right? So if you have carbon and H, then you have the aldehyde. So that's it. That's like for us now is going to be the edge, so to speak, right, of this knowledge. And then, yeah, we'll continue like further with further connections, right, when we go to like other chapters, right? So, but that's for the future. So, yeah, that's like our options, right? So maybe you'll have something like this, right? So let's start with something simple. So maybe that's like one option, right? So this one will be, okay, carbonyl H, right? So that's an aldehyde, for example. So I can just put some like general terms here, right? So that's an aldehyde. And then as like one of you mentioned, so in the middle, right? So you need to have the CO in the middle, carbonyl in the middle. So then, well, you can like do something like this, right? So maybe it's going to be, let's start with like a very simple ketone. That's pretty much the first representative of the ketones. Ketones, it's going to be like that, right? So this one is known as, it's a ketone, right? COC, right? So you can see this pattern. So this is going to be our ketone in general terms, right? Or also known as acetone. So that's like a very common name, right? Accepted, just like you have like toluene, for example. Or you have, what's it called? Benzoic acid, right? So it's a common name. So that can be used legitimately in like your scientific communication, so to say. So yeah, those are examples. And what else do we have here? So we can indicate the, just like according to Lucas, right? So we'll need to show the two lone pairs. So like we can show them here and then there, right? So same thing will happen with the aldehyde. So it's pretty good. So then what else can you like add here? So let's think about other questions. Now that's for you to answer. So the question will be, all right, so let's take a look. All right, so here we go. A new question, right? So for the review, okay, so what is the hybridization hybridization and geometry of the carbonyl carbon, right? So that's another question. So the carbonyl carbon is going to be this one, right? So like with the red arrow, what's the geometry and hybridization here? So also think about the maybe partial charges, right? Let's use the blue color, for example. So you have the partial charges in the carbonyl group, so which is going to be represented as deltas. So oxygen is more electronegative, carbon is less electronegative, right? So then I'm going to do something like that, right? So and then let's see if it is correct. That's going to be the next question here. So what's the hybridization and geometry, right, on the carbonyl carbon? That's the first one. So like, and then we'll later on think about the blue stuff. So what's the hybridization on the carbonyl carbon? Let's take a look at this, right? So, all right. So like we have some responses. Okay, well, great. So a bunch of them came in. So this is going to be indeed sp2, right? So yes, you're correct. You will have sp2 hybridization because you have a double bond and then two single bonds, right? So that's what kind of leads you to the conclusion that it is an sp2 hybridized carbon. So we made a chart in the past of various hybridizations and geometries, right? And then also, in addition to that, you are going to have what? Trigonal planar. All right, so that's well done. So you have trigonal planar geometry, right? So that's for the carbonyl carbon. So now let's take a look at the blue partial charges, and then the question will be pretty straightforward, right? So it is about the mistake that was made here, right? So what is wrong? What is wrong with it, and how to correct it. Okay, so now, so by it we mean in this like most recent question that's been asked is okay, so that's the blue partial charges, right? So what's wrong here? So you have delta minus on the carbon and then delta plus on the oxygen. So let's see if we can catch this error and then rectify that. So here you can kind of again think back to your previous experiences, right? So that's a review in a lot of sense. So what's like wrong here? Delta minus on the carbon, right? And then delta plus on the oxygen. So is it how it's supposed to be? So now that's kind of like the question, basically. All right, so we have some responses coming in already. So people are getting after those questions. Good job. All right, so let's see what we have. All right, so and then, so basically the conclusion is the charges are flipped, right? So they will need to be switched, right? And then people say that O should be more negative and then carbon will be more positive, right? So yeah, that's pretty much the case, right? So indeed we'll have delta plus on the carbon. It's less electronegative, so it kind of like loses electron density and becomes partially positive, right? So lose negative, become positive. So and then this guy will have to be minus, right? So it's going to be like delta minus, it's like huge minus there. So because oxygen is more electronegative and kind of like gains electrons towards itself and becomes partially negative, right? So that's what we will get. And yeah, pretty much that's what we have, right? So you have your other examples, right? Here specifically on this slide, some kind of compounds, right? So, and then other groups you can also see, right? For example, it's an alcohol, right? So here a bunch of alcoholic groups, right? So in this case, so you have quite a bit of them. So, but that's what you will see in a lot of cases in like organic compounds, right? So these are the arrows for the alcohol functional group. You have COH combination everywhere. So, and you have the carbonyl, so which is kind of in this lighter blue color. So yeah, that's what the carbonyl group looks like. So, and then you will have chances, I guess, also to draw that a lot as we get to activities for this worksheet. So we'll see what we can cover. So then that's the difference between aldehydes and ketones. So we have some more examples here. So aldehyde must be like C, carbon, then CO, carbonyl, and then H, right? So that's going to be your kind of like situation, right? So then what else? For the ketone, you will have that situation. You will have here, as we see on this slide, you are going to have a carbonyl carbon attached to like two other carbons, right? So, and yeah, that's it. So it's okay to show the connection like this. So that's fine, right? So the kind of like knowledgeable person in this course will know that the bond is between carbon and carbon, right? So it doesn't have to be, it cannot be between carbon and H somehow miraculously, right? So that will not happen. That's a carbon-carbon bond. So sometimes, so if you are not like happy with that, you can show it as such, right? It's going to be H3C, then you have your carbonyl carbon and then methyl again. So it's more explicit way to show this carbon-carbon bond. So it's also okay. So then, yeah, and then one more thing about the like alcohol stuff, right? So notice how we draw the alcohols. It was like showcased by one of your peers, right? So if we have some kind of like alcohol, right? So like isopropanol. So, and then it was like, okay, well, we have this OH, right? So the bond, don't show it like from this carbon to the middle, right? Show it like this, right? So now it's a clear bond between carbon and O. So, and then if we try to do something like this, that's what you did, something like that. So that's kind of going to be like not so good, right? So like, let's not do this. So basically carbon O, like more direct bond, just kind of like do that, right? So we had this as a kind of a thing when what we shouldn't do. There was one slide about like do's and don'ts. So just kind of like take a look at that, please. But yeah, we want to show here explicitly the bond between carbon and oxygen. That's just how the convention goes, right? So if you like start drawing it in some kind of software, so it will not connect your carbon in the middle somewhere, right? So it will be like directly from carbon to O. So just kind of some things to keep in mind, right? So, but you will see them over and over again, and yeah, that's going to be okay. But yeah, overall, just like some minor items from the past. So now the naming, right? So these are the rules how to name aldehydes and ketones, right? So in all cases, looks like we are going to start with the longest chain, right? So that will contain the functional group. So what's it called? The root of the name will be based on the parent alkane, as we call it, right? So if you, for example, see the longest chain with, let's say, 7 carbons, right? So that's gonna mean that we are going to have, let's just start drawing here, right? So maybe we'll see some kind of chain like that. 1, 2, 3, 4, 5, 6, 7, right? So 7 carbons. So if you look at this, so for now, it is just the alkane, like strictly speaking, right? So because nothing is attached to that, there is like no substitution of the H's happened. And then you have the alkane with 7 carbons. So this will be called in a particular way, right? So actually, let's try to recall it. So let's see if you remember that. That's like the most important thing, right? So let's do the question, right? So like what is the name, right? So of the alkane here, alkane on the piece of paper, right? So here under the document camera. So this one, right? So count the carbons here. What's going to be the name, right, in this situation? So that's what you will use, right? Once you get to the naming of aldehydes or ketones, because they will inevitably contain some kind of like longest chain, which will be based on the name of the respective alkane, right? Except we're going to, of course, change the suffixes and like add some numbers to show where the stuff is present, right? So that's basically how it goes in terms of nomenclature, right? So like, what is this guy? All right, so and this one is let's see what we have. So it is a heptane, great. So you have 7 carbons, it is a heptane, right? So then for the, if you have the aldehyde, right? So maybe you will have the aldehyde. So as you said, it cannot be in the middle, right? So you cannot kind of like put like COH somehow to this carbon, right? So it will just not happen if you try to make like the carbonyl group here, right? And then H, you'll like end up having a pentavalent carbon, right? So then aldehydes will be on the end. So here or there, right? So just kind of like, okay, well, let's make it into an aldehyde like so, right? So now we can show the carbon for our learning purposes, just to kind of solidify the fact that, okay, well, there's a carbon here, right? So, and now you have your aldehyde, right? So the name will be like this, right? So so we need to also start numbering the carbons, right? So from the name, which is from the end, which is closest to the aldehyde or keto group, right? So in this case, we'll be numbering from this end, technically from right to left, 1, 2, 3, 4, 5, 6, and 7. 7 carbons, right? Right now, we don't have any substitution on the chain going on, right? So, but we are going to use the root, which you gave me, heptane, right? So, and then we're going to use the suffix al, right? So it's going to be heptanal, right? So which will stand for the aldehyde naming, right? So that's how it was like proposed to name them. So heptanal is your compound, right? So there is no need to say it is like one heptanal because you can only place the like aldehyde group in one place, right? So if you put it here, right, so then you'll have the same molecule, right? So nothing will change. So no matter what you have here, so you're going to only place like carbon with the like aldehyde functional group on the terminal carbon, right? You cannot have it like somewhere in the middle. So then what else? So let's say if you are going to have some sort of substitution happening, right? So maybe on carbon number 3, you are going to have like that, right? So let's just put this group here. So in blue. So what's this group, right? So which is in the blue color. So let's collaborate on that and see what happens, right? So it's going to be another question. So what is it, right? What is it? So here we go. Lots of questions in the Google Classroom today. What is this group in blue, right? So right now it looks like a tick to like some people. So, but for us, it needs to be kind of like it needs to bear a particular meaning, right? So, like, what does it mean, right? So this blue group. So it can be encountered at like grocery shops, for example, right? So like when you are buying the rubbing alcohol, I think. And now we have it here, right, in this particular picture. So like, what's that blue group, right? So let's try to recall the name for that. Okay, so what do we have here? What is it? All right, so, oh, we have a bunch of responses on unbelievable. I mean, surprising. Okay, and this group is an isopropyl. Great. So it is isopropyl and it's not a ketone. So there were some votes for the ketone, but you don't have the oxygen here, right? It's CH3, CH, and CH3 again. So there is no carbonyl. So it could be looking like a part of acetone, right? So, but it's not. So the best case to call it is going to be isopropyl. So good job. So this is isopropyl. So just kind of, again, check your like, atoms, so to speak. And then that's isopropyl. So if we want to say that, okay, well, in this aldehyde, there is isopropyl, it's going to be already kind of the functionalized. We have the functional group, such as isopropyl, or a substitute, could be called a substituted aldehyde, substituted heptanal, right? So then we can say, well, on carbon number 3, there is an isopropyl, right? 3 isopropyl, 3 isopropyl, heptanal, right? So that's going to be the name of our aldehyde. That's basically kind of as far as we go, right? So for the ketones, it's going to be a little bit different, right? So it's going to be step 3 in this set of rules. So we need to have the suffix "-one", right? So if we have a ketone. So now let's draw some sort of ketone. So which one? This one will contain, let's say, a little bit different number of carbons. So let's make it like this. All right, so now who is this, right? So that's going to be the question for you again. So and then it's going to be the question, right? So like what is it, right? So that's the question. That's your previous knowledge. So that's just going to be looking like a bunch of squiggles, right? So, but in fact, it has a more profound meaning than we might think. So, like, what is it, right? So, I've been grading exam 2, so it's going to be available a little bit earlier this time around. So hopefully even, I don't know, sometime on the weekend, but by Monday for sure, you can stop by and then grab it. So lots of people did good with the nomenclature this time around, but sometimes it was like off the track, right? So that's why we try to like review those things, and then hopefully they'll prompt you to review something, right? So nomenclature in particular. So who is this, or what is it rather, right? So let's take a look. Okay, so good effort going on, and it's going to be octane unambiguously or unilaterally. People say it is an octane, right? So now, as somebody mentioned in the chat, so Ari, so they were saying that we have the ketone in the middle, right? It needs to be like in the middle, and then we can like put it maybe like here somewhere, right? So that's going to be ketone, right? So because you have C, carbonyl, and carbon again, right? Or maybe you can put the ketone here, for example. Let's just put it in this like random place, right? So that's the one. So you have a ketone here, right? So that's a possibility, and then you are going to have C, CO, and C. It's going to be like somewhere here in the middle, as it was mentioned in the past. So now here you have it, right? So you need to start naming, right? So this is kind of like not quite in the center. It cannot be because of the like even number of carbons, right? So and then here you go. So if you start naming from here, it's going to be 1, 2, 3, 4, 5, right? So it looks like carbon, carbonyl carbon, or the keto carbon is present on carbon number 5. If we start naming right to left, okay, so in the like, Middle Eastern way, then it's going to be 1, 2, 3, 4, right? So that's going to be better. So because we are going to like have a smaller number for the carbonyl carbon of the keto group, right? So let's just go right to left, and then it's going to be okay. So this is going to be like carbon number 4. So you have like 1, 2, 3, 4, 5, 6, 7, and 8, right? So that it's based on octanone. I mean, it's based on octane, right? So this root will be retained. So it is octane, octane, right? So, but since we have the ketone, we are going to use the suffix "-one", right? Like so. So that's your suffix "-one". And then here we need to show the number, right? So where the ketone, where the carbonyl carbon of the ketone is located, right? So that's what we are after. So it's going to be this kind of like maybe like red carbon, right? And then your surrounding keto carbons will be like green and green, for example, right? So that's the way to visualize it. So then we'll just simply put the 4 here, right, instead of in front of the octanone. And then on carbon number 4, there is a carbonyl carbon that makes the ketone possible in the octane-based molecule, right? So that's the way to think about it. So, but you'll see that more and more in practice, and then it'll become kind of like more understandable, right? On carbon number 4, there is this kind of like carbonyl carbon that forms the keto group, right? And makes the ketone based on the octane carbon like skeleton, right? So then we also might add something interesting here. So maybe let's do something like that. So here we go. So let's add this guy, right? So because why not? We have seen it already in the past. So, and that's going to be that group, right? So now let's try to name it. So, and we are going to name the entire compound, right? So considering the functional group here. So, and the question is name the compound, right? Name the compound. Please, I'll say it verbally. So name the compound, please. So that is your something octanone, right? So 4 octanones. So it means that on carbon number 4, we have the carbonyl carbon that like makes the ketone group possible. And then also we have some kind of other things, right? Such as this hexagon all of a sudden with double bonds and everything. So what is happening there, right? So like who is that, or like what is it rather? So that's up to you to decide. Okay, so we have some responses happening already, so good effort here. All right, so like what's going on? So like who is that, right? So again, mind your spelling, right? Based on the like exams I have read so far. So yeah, the spelling can be an issue, right? So just kind of like put it straight. So like don't kind of like forget the words. There could be typos, that's understandably so, but also just like check your spelling, right? So if considering you have time, so typically people have finished the exams fast so far. Second exam was a little bit longer, so yeah, but still you can like double check your answers. You can use the entire 75 minutes and whatnot. So that's all given to you. And it's going to be potentially helpful. All right, so what do we have here? So we have it's not octane, right? So again, like check your spelling, right? So just like based on what I see right now. So then we have 2-phenyl-4-octanone, right? So good choice, right? So it is 2-phenyl-4-octanone. Great. So then also, if you kind of like think about this green group, right? So it's not toluene. It's close to toluene, right? So that's right. So, but if we think about toluene, it is supposed to be like this, right? So that's toluene. One, two, and then you have like a metal here, right? So that's what toluene is supposed to be, right? So, but if you, in all honesty, look at this compound, so this piece, right? So yes, we have this carbon here, but then it's not CH3, right? So carbon number 2 is not CH3, so it cannot be toluene. So this guy is like not toluene, right? So it is a phenyl. So the green circle piece, it's technically C6H5. If you think about the molecular formula, it is a 2-phenyl, right? So 2-phenyl-4-octanone. Okay, good job. So then we'll have just some more examples here, right? So we have the ketone like that. So 2-butanone. So again, right to left. That's like the way to like number things here because we want to minimize the carbon which possesses the carbonyl making the ketone. So then here, what else do we do? So this one is kind of usually in the middle, right? So that happens because you have the odd number of carbons in the chain. So it's 5, and then you here have the carbonyl in the middle. So no matter how you name it, right, European way or another, so you will get carbon number 3 with the carbonyl making the ketone. So then you will have what else? Methyl on carbon number 2. So here we're just trying to minimize the number of carbon where the substituent is allocated because technically it would be number 4, right? So if you name it like that, 1, 2, 3, 4, right? So but we want to minimize the numbers of the carbons which bear the substituents, right? It's going to be 2-methyl-3-pentanone, but it could have been 4-methyl-3-pentanone, right? So no matter how you count, so the carbonyl will be in the middle, right? So, but we'll have a higher number for methyl substituents. So if we number the chain right to left. So we want to minimize the number as well. So number minimization, 2 is better than 4 because technically it could be like 1, 2, 3, 4, 5, right? So this is like not good numbering. So Then what else? So these are our aldehydes, right? So maybe the first one is like a not substituted aldehyde, just kind of like straight chain of 6 carbons, and it's going to be hexane, something, hexanal, right? So that's going to be our suffix, and then that's it, right? So hexanal. So then next one will be a little bit more difficult, right? So we have 4 carbons in the longest chain, and we have the substituent here. So this guy, right? So that is a methyl, and what we're gonna say, right? So butane, right? So butane, that's gonna be our parent alkane. So aldehyde will be butanal, consequently, and now we have a methyl there as well, right? So it's gonna be, so numbering starts where aldehyde is, right? So like whatever end you have, right end or left end. So the one which has the, what's it called, aldehyde functional group will start the numbering of the chain, right? So here we go again, right to left. So good. And then we're going to be like, okay, carbon number 1 will be the rightmost, and then we'll go to the left. Okay, so 1, 2, 3, 4. So then on carbon number 3, consequently, we have the methyl. So then it's going to be something like 3-methyl butanal, right? 3-methyl butanal, right? So that's our substituted aldehyde. So now let's take a look at some more examples, maybe. So perhaps I would say we'll select some of them. Let's take a look at A, for instance, right? So that's going to be the one. So what do we have here, right? So first of all, let's see if it is aldehyde or ketone. Looks like it is a ketone, right? So because we have our carbonyl carbon surrounded by 2 other carbons, and that's it, right? We have the COC formation of atoms. So it means that you are going to have a ketone, not an aldehyde. So then we will count the carbons, right? So here we have them, right? So this seems to be the longest chain. So how many dots do we have? 1, 2, 3, 4, 5, 6, 7. So 7 dots, right? So if you theoretically look at this one, it will give you 1, 2, 3, 4, 5, and 6, right? So then, yeah, it's shorter. So then the 7 carbon chain will be the longest one. So then this guy will be your substituent, right? So that's the ethyl. Then another one is going to be bromine. So that's what we are dealing with here, right? So let's take a look at the name. So perhaps we'll recall the root, right? For the alkane, this contains 7 carbons, so it's going to be heptane, right? So heptane, heptane. And then since we have a ketone, we're going to use the suffix -one. So then the keto, carbonyl carbon, is located on carbon number what? So we can name it like that, on number 1, 2, 3, and then or this and 1, 2, 3, 4, 5, right? So 5 is larger. So we need to go from left to right, consequently. So then number them as such. So let's use the purple color, maybe 1, 2, 3, 4, 5, 6, 7, right? So then we can say here then that on carbon number 3, there is the ketone carbonyl carbon, right? So that makes the keto group possible. So 3-heptanone. Then we have substitution happening, right? Here, so in this case, we minimize the number for ketone. That's we kind of give the preference to the keto group number minimization, right? So, and then like other substitutions, like whatever happens, happens, right? So this is not a like symmetrical ketone. So the carbonyl group is closer to one and then the other. So then we have ethyl and bromine, right? So here we just need to arrange them alphabetically. Ethyl starts with an E, bromine starts with B, right? So, but bromine will become bromo. So, because that's kind of how it's named when it's a substituent or a functional group, right? So then we'll start with the bromo, right? So bromo will be first, bromo. Then next one will be ethyl, right? Ethyl. So bromo and ethyl, right? Alphabetically, they are arranged. So now bromo is on carbon number 6. So it is 6 bromo. And then ethyl is on carbon number 4. It's 4 ethyl, right? So that's the one. We have dashes here between bromo and 4. and that's it, right? So 6-bromo, 6-bromo dash 4-ethyl, 3-heptanone. So that's kind of like the most complicated thing here that we have. So maybe let's take a look also at an aldehyde, which will be like rather evolved, right? It's a C. So that one is under consideration. So apparently we need to like number the chain from the from right to left. And here we go. So we'll go like 1, 2, 3, 4, 5. That seems to be the longest chain, right? So all good. So then the root will be pentane, right? So because it's based on pentane originally. So, but since you have the aldehyde, it's going to be bearing the suffix al, right? So you have pentanal. So then you will have substituents, right? So this is going to be methyl and chlorine. So what do we have here? So chlorine or chloro will be first, and then methyl will be second, right? So you are going to have here the following thing, right? So chloro is going to be CH, chloro. Then you have methyl, so which will be dimethyl. So because you have two methyls, so dimethyl, dimethyl. All right, so dimethyl. So now let's see, chlorine is located on carbon number 4. Let's start with that. So we'll just say 4-chloro, right? So, and then on carbon number 2, we have the dimethyl thing happening. So this way, so as you recall from like alkane nomenclature, if we have two substituents, two methyls, for example, on the same carbon, so the numbering will be like that. So it's going to be 2, 2 dimethyl, 2,2-dimethyl, right? So basically on carbon number 2, there is a methyl, and on carbon number 2, there is a methyl again. So that's what this 2, 2 stands for, right? So 2,2-dimethyl pentanal. So that's going to be your name. So 4-chloro, 2,2-dimethyl pentanal. So that's the name of this aldehyde. All right, so now let's see. Okay, so now finally to the physical properties we go, and then we are approaching activity number 1, I would say. So you have the hydrogen bonding, right? So that could happen because of the polarity of the bonds, right? So that happens to be present in aldehydes and ketones. So previously, like you told me, so like who is going to be delta plus, who is delta minus. So that's all good. And now, so it's going to be up to you to decide like where those charges are in the respective molecules, right? So it happens to be the case that if you have, let's say, the aldehyde, so and the water, so the hydrogen bonding will be possible, right? So since you don't have let's say polar like atom H what's it bonds in the aldehyde or ketone, the hydrogen bonding between aldehydes, like 100 molecules of aldehydes, will not be possible, right? Or you cannot hydrogen bond, let's say 100 molecules of ketones, right? So because there is no polar atom and H bond, right? So if you look at the best case scenario, will be like maybe like CH bond, right? So in aldehyde, but it's a CH bond. It's not OH or HF or HCl, right? So or NH, which are requisites, prerequisites for the hydrogen bonding formation. So if you look at the ketone, there are only like CH bonds at best, right? So they are considered non-polar. So CH bonds are considered non-polar, hence you cannot, unfortunately, form the hydrogen bonding in between aldehydes and ketones themselves, right? So, but if you have some kind of like a second party molecule, so to speak, then you'll be able to do that as long as contains some kind of polar atom H bond, right? So by atom, I mean like specific atom, such as OH, right? Oxygen. Oxygen H is a polar bond, right? So then you might have also NH, or such as in activities, you have HF and then HCl. So those are like pretty polar, and then they will be able to make the hydrogen bonds, right? So maybe also like NH3, for example, right? So also has polar NH bonds that will be able to make the hydrogen bonding with aldehydes and ketones. So now let's take a look at this activity that brings us to the formation of the aldehyde and HF hydrogen bonds. So here it's going to be a little bit more advanced. So if you want to do this activity, you will need to show partial charges in lone pairs, right? So because it will lead us to understanding how the bonding works, right? Hydrogen bonds in this case. So between some sort of random aldehyde and HF, right? So HF can participate in hydrogen bonding because it has this polar hydrogen fluorine bond. So if you want to give it a try, you might as well do that. So we have one candidate. So let's you go. So we'll do activity 1A, right? So it's going to be aldehyde and the HF. All right. So yeah. And here we go. All right. So let's take a look at this. Since it's Thursday, it's an International Sauce Day. You have an extra incentive. If you work on the board, then you can win the sauce as well. Okay, great. So yeah, that's the ones. And then what about the partial charge on the carbon in the aldehyde? Just kind of for statistics. That's going to be delta plus. All right. So well done. Yeah, that's a ketone.
No, but like with this, like if we were naming it, would that be the same?
Yeah, that's right. So you can name it as a phenol.
Okay.
Yeah. Okay. So anyway, so that's going to be our hydrogen bonding. So now we have B. So we have ketone and HCl. So if anybody wants to give that a try, right? So now we're switching to ketone, but it's still a possibility to form the hydrogen bonding between ketone and HCl. If anybody wants to give it a try, so this is available. Okay, yeah. Let's go and do B, right? So that is, let's just continue on the same kind of like piece of paper here. So you have a ketone and HCl, please. So let's see what happens. So ketone and HCl. Yeah. So then for now, we'll just show the partial charges, right? So like those pluses and minuses will have to be like delta plus, delta minus. So you can just show the delta letters, right? Because we don't yet dissociate them. So yeah, yeah, that's right. So the delta is written like that. So good job. And then you have delta plus still on the H and delta plus, delta minus on the chlorine, right? So because they did not yet dissociate, so they're all partial charges, okay? Good job. And then also what you can do, show us the H's on the carbons, right? Yeah. So we either show no carbons at all, just kind of like bands and termini, right? Or if you show the carbons, then you have to show the H's, right? So that's just how it goes. So otherwise, you just kind of leave it like halfway. So previously we show expanded way all the H's, so that's well done. Okay, yeah, awesome job. So yeah, that's what we'll have for the hydrogen bonding. Okay, well, looks like you got it. All right, so now let's take a look at the physical properties a little bit more, right? So this is just a trend which was determined experimentally, but we can think about the reasons here, right? So basically, so this shows the hierarchy of the strength of the bonds between the molecules. So turns out that, for example, like ethers and alkanes have like very comparable boiling points. So because they are almost like very similar in structure, right? So if you look at this compound versus that, so it's like almost the same structure, like geometrically, but we have the oxygen, right? So somehow like in the middle, and then it's an ether. So because of those similarities, so we have similar boiling points, like 34, 36 degrees Celsius, right? So as we move to the, what's it called? As we move to ketones and aldehydes, so turns out that they will have higher boiling points substantially because of the dipole-dipole interactions, right? So here, so basically you have dispersion forces. They are very weak in the hierarchy of forces. I think it was covered in the previous general chemistries, but if not, then, well, here we go, right? So then you have later on dipole interactions, right? So dipole interactions. A little bit stronger than dispersion forces, right? So they kind of like better, like a little bit stronger. Let's put it this way: dipole-dipole interaction. So and then that lands stronger forces between the molecules, and then consequently you will have to apply higher temperatures to break those forces and then vaporize the molecules. So next one will be the like biggest boiling point, right? It's like alcohol of the comparable size will be like 117 Celsius already, right? Why is that so? Because we have the higher strength. It's going to be hydrogen bonding, right? So hydrogen bonding will be much stronger than dipole-dipole interactions, and consequently you'll have to have even higher temperature to apply to boil the alcohol, right? So that's just what will be happening here. So it's kind of tempting to say that technically you will have also the dipole-dipole interactions in this case, right? So, but looks like they are like weaker in general, and experiments kind of like show that, right? So that this like dipole-dipole interaction between ethers is potentially weaker than the dipole-dipole interaction happening in case of aldehydes and ketones, right? So, but for now, we'll just like remember that, like, okay, well, experimentally, empirically, ethers are comparable boiling points with alkanes, right? So that's like a very nice slide, and that's what we have in hierarchy, right? Of the dispersion forces are weakest, right? Out of those three, then dipole-dipole interaction will be a little bit stronger. It's in the middle, and hydrogen bonding will be the strongest, right? So that's kind of an important force right there. So then what else? This is kind of another trend here showing that like where typically the boiling points of like alcohols will be line compared with like alkanes. Alkanes, you see, you have to have some kind of like huge molecular weight, right? Maybe like 100 or something to get to the boiling point of about 80 Celsius. But if you have like a very low molecular weight alkene, that narrowly gases at negative temperature, right? Whereas alcohols, even like if it's like ethanol is a liquid at room temperature, right? So, and then you need to like achieve about, I don't know, like 60 or something Celsius to boil alcohol, right? So that's why at room temperature, it can be consumed, right? So by people or like animals, sometimes you can also consume alcohol theoretically. But if you put the, like, let's say, alcohol, whatever, like amaretto in cookies, for example, it will boil off and then you will have the almond taste of the amaretto and no alcohol, right? Because it will boil off in the cooking process, which is conducted at like higher than like 60 Celsius, right? So cookies are baked at whatever, 300 Fahrenheit or something. That's above, well above 100 Celsius. And then you boil off the alcohol from the alcohol containing aromatic additives for the cookies, right? So then what else? So here we have it, right? So that's our ranking by the boiling points, right? So if we take a look at part A, right? So here we kind of see the alcohol right away, right? So then we assume that it will most likely be like highest boiling point, right? So then we have the ketone, it's going to be the runner-up. And then finally, the alkane, cyclic alkane will be the lowest boiling point, right? So that's how they're ranked, right? So alcohol, hydrogen bonding, highest, right? Forces. Ketone is a little bit weaker forces because they are dispersion forces and or no dipole sorry interactions in ketones. And then number 3 will be lowest boiling point because it is just dispersion, London dispersion forces, right, in the case of cycloalkane. So now if we have a look at B, right, so here we have basically, okay, well, we'll have alkane, good. Aldehyde will be like alkene probably will be the lowest boiling point, right? It's the number 4 lowest boiling point, right? So then we go a little bit higher, it's most likely going to be the aldehyde, right? So because other molecules are alcohols, so they will be somewhere higher boiling point wise. So then we will have what? So it's going to be like place 4 is going to be alkane, lowest, right? So lowest number consequently out of the 4, then it's going to be number 3 potentially. Now between 1 and 2, right? We need to decide. Well, turns out that you need to count here now the number of OH groups, right? So because basically, if you have more hydrogen bonding capable groups in the molecule, then the interaction between the molecules will be stronger, right? So because if you think about it, so you put together 2 molecules of this, you will have one dotted line as shown by your peers, right? That's what like Megan showed, that's what like Nicholas showed, if I don't confuse the names, maybe I confuse them, right? So only one dotted line, right? So that you can see. So if you take a look at this alcohol, right? So with 2 OH groups, you will have a lot more dotted lines, as in such, right? So maybe let's show it here. So that's your OH. And then you will have like one dotted line, and then you'll have another dotted line. So like for those 2 molecules interacting with one another, you have 2 dotted lines, which basically signify more interaction. If you throw in kind of the third OH group somehow, right, into the molecule, you will have the third dotted line, theoretically. So then consequently, you will have much stronger hydrogen bonding interaction in this case than in that case, right? So if you draw another molecule of this alcohol here, right, OH, then it's going to be something like that. So just one dotted line, one hydrogen bonding bond, right? So it's going to be like a weaker interaction here, stronger interaction there. Consequently, so stronger interaction will give you a higher boiling point out of those like 2 compounds, right? So this will be the top boiling point. This will be the runner-up, number 2. So yeah, so now okay, so more physical properties, I guess, for today. So and then we are going to get to more trends, right? So miscibility, that is what is that about, right? So this is about the how it mixes, how well it mixes with water. So basically, if it's more like water, it's more likely to be miscible, right? Or mixable with water and makes a solution, as some of you pointed out in the past, right? So here, like we have the alcohol, it very much looks like water, except so like 1H was substituted with a famous isopropyl. So these compounds should be miscible with water, right? So that's going to be the OH. So then what else? The other compound is going to be ketone, acetone. So it's less like water, but it is a relatively low molecular weight as well, right? So it has a chance to be mixable with water because of the low molecular weight, and kind of it resembles water because at least it has the oxygen, right, in the structure. If you look at alkane, well, it's going to be not miscible with water. As we know, it doesn't look like water at all. And then this aldehyde also is not miscible with water, most likely, because even though it has some resemblance of water because of the oxygen, right, in it, it has this huge like organic alkane character, right? So which is going to be in this green blob, right? So that's what makes it like very much unlike water, right? So whereas this yellow blob is kind of like not substantial, it's like more in line with the smallness of the molecule of water, right? So then what else? You will also have likely miscibility with between water and this alcohol because it has a lot of water character, like two OH groups. So this one will be miscible as well. Very likely because the chain is relatively small, right? 3 carbons, so it looks like it's going to be fine as well. So as well as that, right? So 3 carbons seems to be like a nice number to assume that, okay, well, you have the miscibility with water between this like molecule, right? So finally, this is your like alkane. Alkanes are not miscible with water because they're not like water, right? So that's kind of like along the lines of that we need to think. And so these like green compounds basically are not like water at all. So they will be not miscible, right? So you kind of need to like make like several judgments as you consider specific cases, right? So then what else? And then if you have nonpolar solvents, such as like hexane, it's going to be common nonpolar solvent, you will have the likely miscibility with the nonpolar solvent if you increase the carbon chain length. Okay, so at this point, I guess we're going to stop. So because we achieved that, and then I'm gonna launch the exit tickets. So if you can fill it out in the Google Classroom, that's going to be great. So let's do that. Exit ticket. Okay, so, and here we go. Maybe, look out. Just a second. Bye, everyone.